Hey everyone, I want to discuss variable and dimension reduction a little bit further because these concepts are mentioned a lot in data analytics, and these techniques and methodologies are extremely useful. And I want to show you how they're derived and where these concepts come from for your future knowledge. Okay, so variable reduction is all about finding this sweet spot with our model where we are not overly complex, but we also don't have a lot of error. So increasing the variables in a model can reduce the unexplained variance, but it increases the model bias and can result in overfitting. Um, we can see that as model complexity increases, the variance of the model increases and the squared bias decreases. The test error also starts decreasing as the complexity increases, but up to a certain point after which it just starts to increase. So our total error dips down and then swoops back up after we start adding too many unnecessary variables. So the whole point is to find this optimal point when we're fitting a model. What is the right variance, and let's make sure that the variance is not too high. So dimension reduction involves more advanced methods for reducing the number of random variables under consideration when we are building a data model by finding the set of principal variables. These might include mathematical models or machine learning or even human trial and error methods. So we use dimension reduction for simplification of models, faster run and training times. Remember, if we're working with a lot of data, it can get computationally intensive. Reducing overfitting, so generalizing our model to work well with all data and not just our training data. Increasing the availability of data, since lower dimensional data is less sparse than higher dimensional data. And eliminating redundancy or irrelevant data from large unmanageable data sets. So remember, we have to store data, and that's expensive, and we have to secure data, and that's also expensive. So we don't want to waste time storing, securing, and analyzing data that we don't need. So we can use feature selection or feature extraction in order to accomplish this goal. Feature selection is machine learning techniques that include filters, wrappers, or embedded feature selection, and feature extraction methods include things like matrix factorization and neighbor graphs. So before we discuss those in more detail, let's talk about the curse of dimensionality. There is an exponential increase in volume associated with adding extra dimensions to a mathematical space. For example, 10 squared is 100 evenly spaced sample points suffice to sample a unit interval or a one-dimensional cube with no more than 0.01 distance between points. An equivalent sampling of a 10-dimensional unit hypercube with a lattice that has a spacing of 10 of 0.01 between adjacent points would require 10 to the 20th sample points, or 10 squared to the 10th. In machine learning, problems that involve learning a state of nature from a finite number of data samples in high-dimensional feature space, with each feature having a range of possible values. Typically, an enormous amount of training data is required to ensure that there are several samples with each combination of values. A typical rule of thumb is that there should be at least 5 training examples for each dimension in the representation. When you have a fixed number of training samples, the predictive power of a classifier or regressor fit first increases as number of dimensions or features used increases, but then decreases, which is what we discussed before. So basically, in higher dimensions, data becomes more sparse, and so the distribution of data points gets tighter until all the data points are all approximately the same distance apart. So that's what we use these normalized distances for. Traditional feature selection methods to reduce variables in a linear regression model might include eliminating all non-significant variables. So we start here first, and then we can do backward elimination, where we start with all independent variables and then remove the least significant ones one at a time, and then stopping when the model statistics do not improve further or worsen. Forward elimination, so we start with the variable most expected to improve model performance and then add variables one at a time until performance does not improve or worsens. and then bidirectional elimination where we add and remove variables simultaneously. So with a small model, we can do this manually, but as the number of variables in our data set increases and our model becomes more complex, we use machine learning to perform these computations for us. And that's where you might hear these terms of filter, wrapper, or embedded feature selection. We don't need to get into a lot of detail here, that we can save that for another class, but basically it goes through one of these techniques, one of which might filter is computationally faster, but the solution is not specific to your exact problem. Wrapper is very computationally intensive, but also very accurate for a particular problem. And then embedded is built-in feature selection when we construct a model, and it basically penalizes the coefficients of our variables that aren't effective, shrinking most of them to 0. For feature extraction, we need to think about matrices and matrix factorization. So if you recall, data in the form of n by d grid X, or a matrix of size n by d, can be a product of two smaller matrices, so U and V. And our data can be factored into a representation multiplied by some archetypes. So these are U and V are the forms used to reconstruct the data. X will then be approximately U times V, where there is some loss that occurs, and we can minimize that loss function. So one row of data can be broken into a linear combination of a single representation times each archetype. So X can be approximately represented as the product of U and V, which results in some error, and we seek to minimize that error. And that is where we get principal components analysis. So high dimensional space containing many, many observations can be mapped into a new space where the first principal component is just a vector, which describes the maximum variance in the data. And then subsequent components are linearly uncorrelated with each other. So the first vector is the eigenvector with the highest eigenvalue, if you remember those terms from linear algebra. And then each subsequent component is orthogonal to all other preceding components and represents the highest remaining variance. So we're trying to capture as much information about the data as possible in our principal component vectors, and reduce the dimensions based on that information. So our general optimization problem was to minimize that loss function. And for principal component analysis, the loss function is the mean squared error of our model, of our regression model. So there are no constraints. If we add constraints, we change the method. So there's a method called sparse PCA, which uses that same loss function of mean squared error, but adds constraints. So it adds these constraints on U, and sparse PCA basically sets to constrain how many archetypes you use, which makes the process more manageable when you're working in many dimensions. So the first constraint we are working with is unit vectors, and the second represents the norm of U, which is defined as its number of non-zero components. So the optimal value is known as the k-sparse largest eigenvalue. And if you were to set k to big D, we're back to ordinary PCA, big D. And the optimal value is the eigenvalue of the covariance matrix. So the thing about sparse PCA is that we can't guarantee orthogonality between components without imposing additional constraints. But what if we constrain further to one non-zero archetype per row? So now U has one non-zero entry per row where the index in that row is the cluster label and the archetypes are the cluster centroids from k-means. So basically, we've taken PCA added these two constraints, and now we have k-means clustering. All right, and then you may also hear about neighbor graphs. Neighbor graphs contain a more diverse variety of algorithms, which seek to cluster points according to distance by neighbors, and they push the nodes on the edges together and the nodes that are not on shared edges apart. And then they calculate those distances and try to optimize those calculations. So basically, you're building a graph and then using force-directed graph layouts. So this is a totally different approach to the very mathematically exact method of PCA. So if you know anything about isomaps, that would be kind of an early approach to the neighbor graphs problem. And basically, we're still using eigenvectors, but more advanced methods basically just work on improving the weighting. So k nearest neighbors weights by Euclidean distance or ambient distance, for example. So whenever you hear these like k-means clustering or k nearest neighbors, this is where all of those techniques originate from, is from these calculations meant to help with dimension reduction. And then finally, there's an even more complicated method called t-distributed stochastic neighbor embedding. And it works by taking your KNN weighted edges by kernel with bandwidth adapted to the k neighbors, and then normalizing the outgoing edge weights so they sum to 1, symmetrize by averaging edge weights between each pair of vertices, and then renormalizing so the edge weight is 1. And if none of that sounded like English to you, it's totally fine. The point is how you weight the edges matters when doing neighbor graph methods, and by doing it well, or in order to do it well, you need a lot of complicated math and operations, and that is why you end up with gibberish like what you see on this slide. So I hope that this was at least a little bit enlightening for you, and yeah.